Hello, this is Professor George Easton. In this video, I'm going to teach you about one-way analysis of variance, usually just referred to as Way ANOVA. Now, before I begin, I'd like you to note that this video builds on the ideas of factors, levels, and replicates, and also on the two-sample student's t-test that I've covered in the latter half of a previous video, which was titled Introduction to Experimentation in Six Sigma and Simple Two-Sample Tests. So in that previous video, we looked at a situation where we had one factor and two levels. But what if we have one factor and more than two levels? In order to deal with more than two levels, we need one-way analysis of variance. One-way analysis of variance is a generalization of the two-sample t-test that allows you to deal with more than two levels. Looking ahead to material that we're going to cover, if you have two factors, you're going to need to use two-way analysis of variance. For three factors, you'll need to use three-way ANOVA and so on. But in this video, we're just going to focus on understanding one-way ANOVA. Now, you have almost certainly seen an analysis of variance or ANOVA table before. And the reason is that an ANOVA table is always a part of the output from any least squares regression analysis. You may recall that in least squares regression, we compute a sum of squares total and decompose it into a sum of squares regression and a sum of squares error. In fact, the formula is that the sum of squares total is equal to the sum of squares regression plus the sum of squares error. Sometimes this sum of squares regression, the SSR, is called SSM for sum of squares model or something similar. But the basic idea is that you are decomposing the total sum of squares into a sum of squares that is fit by the regression plus a sum of squares which corresponds to the error. In regression, these sums of squares are then converted into mean squares by dividing by their degrees of freedom, and then into an F statistic, and this F statistic is used to test if the model is getting any fit. So I have some examples here. This is a simple example in which the weight of 220 students was regressed against their height. So height is used to predict their weight. And this is the output from Excel. And you'll notice that the coefficients are right here. This is the coefficient table. And the table at the top addresses the issue of how well the model fits. It includes things like the R squared. But this table in the middle is labeled ANOVA. And in this ANOVA table, there's a column labeled SS for sums of squares. And there's a total sum of squares, and then a sum of squares regression and a sum of squares residual. These sums of squares are converted into mean squares by dividing them by their degrees of freedom, which are listed over here. The mean squares are used to compute an F statistic, and the F statistic is used to compute a p-value using the F distribution. Now, in this particular case, we see that the p-value is essentially 0, so that the test is highly significant. So what this means is that the regression has in fact found a significant relationship between the x variable height and the weight. Here's another example. It's exactly the same data set, but the output that I'm showing you is from Minitab. And again, you'll notice that the middle of this output includes an analysis of variance table with the same information as in the Excel output. So we have the source is the total, residual or error, and the regression. Here are the sums of squares, the degrees of freedom, the mean squares, the F statistic, and the p-value. So you have seen analysis of variance tables before, so don't let what we're about to do seem newer to you than it really is. Now, as you know, in Six Sigma, we often talk about the y's and the x's of a particular problem or situation, and we think about y being equal to fx. And I've generalized this idea a little bit to say that we oftentimes think about situations as y is equal to fx plus some kind of random error that reflects the messiness of reality. In statistics, we often think about things in a very similar fashion, but the way we generally say it there is that the data is going to be equal to fit plus residuals. And this, of course, is what you have used when you have used least squares regression to fit a data set. In that case, the data is equal to a least squares fitted line plus the residuals. Now we're going to use this idea in one-way analysis of variance. In particular, in one-way ANOVA, the fit has a specific form. The fit consists of an overall mean or grand mean plus an effect due to the factor. So our fit has this particular structure. Saying the same idea but using the terminology of analysis of variance, we're going to view the data as being equal to a grand mean plus a main effect due to the factor, and the two of those together are the fit plus then the residuals. So that's the way we're going to be looking at the data. And then the idea in analysis of variance is that we're going to use sums of squares and f-tests to test whether or not there is a significant difference between the groups that we're looking at. And remember, we're using analysis of variance when we have at least 3 levels, which will give us at least 3 groups. Now, if you go and look at pretty much any textbook on analysis of variance, you're going to see a whole bunch of formulas that look like the ones that I have on this page. You're going to see formulas for sums of squares, for degrees of freedom, and so on. And then you'll see, in addition, formulas for the F statistic that can be used to test whether or not there's a significant difference between the groups. These formulas, however, are quite complicated and not especially intuitive. So that makes me think, how can I make this simpler? Well, it turns out that I can show you how all of this works and what it means by using the idea that in one-way analysis of variance, the data is decomposed into a fit plus residuals, and this fit has the structure of a grand mean plus a factor main effect. And I'm going to show you all of this using an example in Excel. So I've opened up the example Excel file and gone to the tab labeled One Way, which contains the data that I'm going to use to demonstrate one-way analysis of variance. These data are from the Six Sigma Handbook, 4th edition, on page 480. The data represent runs from 3 different machines, and higher values are better than lower values. So we can see that there are 5 observations that were taken from machine A. There were also 5 observations taken from machine B, and similarly 5 observations taken from machine C. Now I want to note a couple of things. First, this experiment was completely randomized. So the way this experiment was conducted conforms with some of the ideas that we discussed in an earlier video. Second, for each machine there are 5 replicates. However, for one-way analysis of variance, there could have been different number of replicates for each machine. For example, we could have had 5 replicates for machine A, but then 6 or 8 or 10 or whatever, a different number for machine B, and so on. And in one-way analysis of variance, having different numbers of replicates for each level of the factor does not affect the calculations in any way. So what we're thinking about doing is decomposing the data into a grand mean plus a main effect plus a residual. So I'm going to begin by just copying the data over under this equation that I have written here, and I'll do that just by using an equal sign. And then I'll use Control C and then select the cells below and Control V, and you'll see that I've just copied all of the y values from the original data set into this column labeled y. Now, the grand mean is just the overall mean of the data. So I can compute that by putting in average and then selecting all of the y's because it's just the mean of everything. And I'm going to want to slide this formula down, so I better put dollar signs in front of everything, which I can do by hitting F4. So this range now, E9 to E23, is an absolute reference to the range of y values highlighted in the box, and that won't change as I copy this formula into other cells. So we can see that the grand mean is 2.267 essentially, and now I'm just going to go ahead and copy that formula all the way down. So far all we've done is take each of our observations and represent it by the grand mean. So now we move to the main effect, which is the second part of the fit in our decomposition of the data. So the way to think about the main effect for an observation is that it's the average of all of the y values for observations which are like the current observation. And what I mean by like the current observation in this case is that they all have the same level of the factor. And then you subtract the grand mean. So what I want to do is look at my current observation. I see that it has level A of the factor. I then want to average all of the y values for observations that also have level A of the factor, and then I want to subtract the grand mean. So I can do this using the average if command. So if I put equals average if, and the way this formula works is I select the range that I want to use to pick the observations that I'll average. So that's going to be the values of the factor, and then I'm going to go ahead and hit F4 because I want this reference to be an absolute reference that won't change when I slide the formula around. And I only want to pick the rows here that correspond to my current observations factor. So I've reached over here and clicked on this cell C9 because that is the level of the factor for this first observation. So what I'm saying here, if I'm taking the point of view of the observation, is that I want to average all of the y values that have the same factor level as my own. Now the last thing that goes in this command, average if, is going to be the data, the column, from which I want to extract the data to do the average. So we want to average things out of column Y, and again, because I'm going to want to copy this formula down, I'm going to hit F4 to put dollar signs around the range and make it an absolute reference. So I'm going to go ahead and hit enter, and what this number 6 is the average of all of the observations that have the same factor level as observation 1. Now that's not quite the main effect. That's the hard part of the main effect. To actually get a main effect, what I have to do is subtract off the grand mean. So what this number 3.73 is saying is that the fit predicts that the y value for this observation is going to be 3.73 units above the grand mean. So now I can go ahead and take this formula and copy it down. So what you can see is that this main effect is the same for all observations that have the same level of the factor. So it's the same for all observations labeled A here for the factor, but then it changes but is the same for all of the observations with factor level B, and so on. So if I take the point of view of the observation, what the main effect is, essentially, the way I like to think about it, is it's the average of everything like me minus the grand mean. What the main effect represents is how being at the factor level corresponding to the observation changes the predicted value of the model from the grand mean. So for example, in this first observation, we're at factor level A, and that means that the model predicts that we'll be 3.73 units higher than the grand mean. If we look down here at one of the observations that corresponds to factor level B, you'll see that the model predicts that on average we'll be 0.467 units below the grand mean because there's a minus sign. And then finally, for observations with factor level C, the model predicts that we'll be 3.267 units below the grand mean. So again, there's a minus sign here. So that's both how to think about calculating the main effects. They're the average of everything like me, if you're taking the observations point of view, minus the grand mean, and also how to interpret the main effects. The interpretation of the main effects is that they're showing you how the various factor levels change things from the grand mean. Now the residual then is just going to be the difference between the data and the fit. So I'm going to put in an equal sign here, go over and grab the data value, the y value, and then I'm going to subtract from that the fit, but the fit is the sum of two terms. It's the grand mean plus the main effect. So I now get the residuals, and I can go ahead and copy those down. So the residual then is just the difference between what is predicted by the fit and what actually happened. So for example, for this first observation, what actually happened, the y value that was realized, is 2 units below what is predicted by the model. As another example, if we look at this observation, you can see that what actually happened in this case was 2.2 units above what was predicted by the model. Now I can do a little bit of checking here because the sum of the main effect and the sum of the residuals ought to be 0. So let me just check that to make sure that I haven't made some kind of calculation error. This is a very useful thing to do if you are actually doing this kind of calculation in Excel, because you'll pick up mistakes that you make. So we can see that the sum of the residuals comes out to be 0. The sum of the main effects comes out to be 1.15 times 10 to the minus 14th, which is 0 for all practical purposes. And so I have in fact checked now that the main effects sum to 0 and the residuals sum to 0. So I'm now going to go ahead and label this row so that I don't get it confused with other things. So I'm going to call it check sum equals 0. And I will left justify that. So now it's time to compute the sums of squares that we will use in testing whether or not there's a difference between the groups. So I'd like just another bit of room here, so I'm going to go ahead and insert a row. And now the sums of squares are very easily calculated. The sum of squares for the main effect is literally just the sum of the squares of all of the numbers in this column. So I just need to go through this column, take each of these numbers, square it, and add it up. So let's go ahead and do that, and I'm going to go ahead and label this. This is the sum of squares for the main effect. Fortunately, there's a function in Excel that will square the entries in a column and add them up. It's called sum SQ, sum square. And so I can just trace out this column and close the parentheses. And so I can see that the sum of squares due to the main effect is 124.13. Now I can also get the sum of squares error from the residuals using exactly the same formula. So I can just go ahead and copy this formula. So I am typing Control-C on the keyboard. I'll select the cell below SSE and do Control-V. And I can see now that the sum of squares error is 28.8. I'm now in a position to start building my analysis of variance table. My analysis of variance table will be based on a sum of squares for the main effect, a sum of squares for the residual, and a sum of squares total. The sum of squares for the main effect is just the sum of squares that I just calculated. So I'm going to copy that down into the ANOVA table just by using an equal sign and selecting the cell. The sum of squares for the error or the residuals is just the sum of squares that I calculated from the residuals, so I'll just copy it down. And then the sum of squares total is just the sum of those two. So I'll just add those up. Now my procedure in constructing this ANOVA table is going to be exactly like what was done in the ANOVA tables in regression. I'm going to need degrees of freedom, and I'll talk about that in just a second. I'm then going to compute mean squares by dividing the sums of squares by their degrees of freedom. I'll compute an F statistic as the ratio of two mean squares, and then I'll compute a p-value based on the F distribution. So the first degrees of freedom that I'm going to tell you about are the degrees of freedom associated with the sum of squares total. The degrees of freedom for the sum of squares total is exactly like it is in regression. Namely, it's going to be the number of observations minus 1. So I'm going to go ahead and put in an equal sign, and I will actually count the number of observations. So I'm going to select now the Y column here. I'll close the parentheses. So count E9 to E23 will give me the number of observations. But the degrees of freedom for the sum of squares total is the number of observations minus 1. So I just added a minus 1 now, and I'll hit enter, and we'll see that the degrees of freedom is 14. The degrees of freedom for the main effect is always the number of levels of the factor minus 1. So in this particular case, we have 3 levels of the factor. The factor was machine type, and we had 3 types of machine, type A, type B, and type C. So the degrees of freedom for the main effect is going to be 2. And then finally, the degrees of freedom for the residuals is always going to be the difference between the degrees of freedom for the total and the degrees of freedom for the main effect. So I'm going to compute that by putting in an equal sign, grabbing the degrees of freedom for the sum of squares total, and then subtracting the degrees of freedom for the main effect. The mean squares then are just the sums of squares divided by the degrees of freedom. So I can calculate that by putting in an equals, grabbing the sum of squares, and dividing by the degrees of freedom. So you can see that the mean square for the main effect is about 62.07. Now I can go ahead and copy that formula down. Now I've gone ahead and computed the mean square for this sum of squares total, but in many analysis of variance tables that number is omitted, and I guess I'm going to go ahead and do that in this case as well. So I'm going to delete it so that there's no confusion about how I compute the F statistic. What the F statistic is the ratio of the mean square for the main effect to the mean square for the error. And so in this particular case, it's 25.86. And what this statistic represents is how much variation in the y's, as measured by the sum of squares total, was explained by the model in comparison to what's left over as random noise. So if what was explained by the model was entirely random, we would expect the mean square for the main effect to be essentially the same size as the mean square for the residuals. and we would expect this F statistic to have a number in the range of 1. In this case, you can see that the F statistic is a lot bigger than 1, but we don't know yet whether it's big enough that it represents a significant difference between the machines. To say it in another way, that it indicates that the main effect is significant. Now, I want to caution you that this F statistic is not like a T statistic. You can't just look at it and decide whether or not it's significant by comparing it to the value 2. To interpret it, you really do need to compute the p-value. I'll also point out that this F statistic is always positive, unlike a T statistic. But the point is, it's different, and you just can't use an arbitrary number like 2 standard deviations to try to interpret it. This F statistic has an F distribution, and large values of this F statistic indicate that the main effect is significant. So to compute the p-value, what we want to do is compute the probability of everything larger than this F statistic, so everything larger than about 26 in this case, using the F distribution. So to do that, we're going to put in an equal sign, and then because we want an upper tail probability, we're going to put in 1 minus. The distribution we want is the F dot dist. We're computing the probability of being above the value of the statistic that we actually observed, which is the 25.8. So I'll put in a comma now. Now the F distribution depends on the degrees of freedom of both the numerator and the denominator. So it's kind of like a T distribution in that it depends on degrees of freedom, but the T distribution only depends on 1 degree of freedom. The F distribution here depends on 2. The degrees of freedom for the numerator, which go in first, and the degrees of freedom for the denominator, which go in second. Those are the degrees of freedom for the residuals of the error. And the very last thing I need to put in here is true, which tells the F distribution function to return the probability that we're looking for. I wouldn't worry too much about this true argument. Just know that you have to put it in. So now when I hit enter, I'm going to get a p-value for the test. And you can see that this p-value is roughly 4.5 times 10 to the minus 5. To make this a little bit more interpretable, I may want to format this number in a different way. So I'm going to go ahead and right-click and pick Format Cells. And instead of scientific notation, I'm going to pick a number. Let's give it a whole bunch of decimal places. And so I can see that this p-value now is very, very small, much smaller than a typical significance level cutoff of 5% or even 1%. And I should remind you that the way to interpret a p-value is you compare it to the significance level that you want for the test, and if the p-value is smaller than that, then the statistical test is indicating significance. So what we can see here is that the main effect of the machine type is highly significant, and this procedure and ANOVA table has shown that there is a highly significant difference between the machine types. So my goal in going through this hand calculation of one-way analysis of variance using Excel is to try to give you a reasonable level of understanding of what analysis of variance is and what it does. So by going through this hand calculation, I'm trying to convey the meaning of all of these formulas, which I think by themselves are essentially unintelligible. Now I've tried to do this by looking at the whole problem of analysis of variance as decomposing each observation individually into the components of its fit, which for one-way analysis of variance is the grand mean and the main effect. And I've explained the main effect to you from the point of view of an individual observation, so to speak. The main effect is just the average of everything that's like me minus the grand mean. Once I take this point of view of decomposing individual observations, then my sums of squares are simply the sums of the squared values in these columns. And what happens is all of the complexity of those formulas simply goes away. So that's been the goal of what I've been describing here. As I say, it's to give you a reasonable level of understanding of what analysis of variance does. In practice, of course, you're not likely to compute your analysis of variance by hand, although you certainly could, but you're much more likely to be using a statistics package. So I thought I would go ahead and show you how to use the ANOVA function that comes with Excel. Now, to use this ANOVA function, we need to organize the data differently than I did when I was decomposing the individual observations in the example as I've done it so far. What Excel is going to be expecting are columns that correspond to each of the levels of the factor. So, for example, this column labeled A corresponds to the results for machine A, and there were 5 of those and so on. As I indicated before, in one-way analysis of variance, I can have a different number of replicates for each level of the factor. So these columns here could be of different lengths. In this particular example, they just happen to all be of length 5. Now, to run analysis of variance, I'm going to go to the Data tab, and I'm going to look for something called the Analysis Tool Pack. And right now, this is not installed into my version of Excel, so I want to show you how to install it. What you do is you go to the File tab, and then to the Options, and then to Add-ins. Now, I'm doing this in Excel 2013, but the process is very, very similar in earlier versions of Excel, and I don't think you'll have any difficulty figuring out exactly how to do this in your version. Now, once I click in Add-ins, I will go to the bottom here where it says Manage. I do want to manage the Excel add-ins, and then I'm going to go ahead and click Go and check the Analysis Tool Pack. I don't need the Analysis Tool Pack VBA, just the Analysis Tool Pack. And then I'm going to go ahead and click OK. And you'll see that what's happened is that data analysis has been added to the ribbon here under the Data tab. So I can now click on Data Analysis, and incidentally there are a lot of useful functions here in addition to analysis of variance. But what I want to do is scroll up and find ANOVA single factor. Then I'll go ahead and click OK. I need to select the input range, and the input range that I'm going to select is all of the data, including the labels. Now, if I had columns here that were of different lengths, I would take this range down until the longest column was covered, so there'd be blanks in some of the other columns. But I want to be sure that I'm getting all the data. So I'm going to go ahead and open this up. Now, I have included labels in the first row, so I better go ahead and check this box. I can use an alpha 05 significance level, and I want to put the output into this same spreadsheet. So I'm going to click on the output range here, and then I'm going to select in this box and select a cell where I would like the output. And then I can go ahead and click OK, and Excel will calculate a one-way analysis of variance. And so you'll see here, for example, that the F statistic computed by Excel is 25.86111, which is exactly what we got before. You can go back and check. And that the p-value is 4.46 times 10 to the minus fifth. And again, that is exactly what we got before. If I very quickly change the format of this to a number with 7 decimal places, which is what I used before, you'll see that I get exactly the same value for the p-value as I did when I did the calculation by hand, so to speak. So this is how you run a one-way analysis of variance in Excel using the Data Analysis Tool Pack. Before closing, I wanted to point out that I've included with this video another Excel file that I've heavily annotated to show all of the calculations that I demonstrated earlier in this video, showing the decomposition of the individual observations and the calculations in the ANOVA table. So you can use this annotated file as a reference for exactly what the calculations are. So this completes my discussion of one-way analysis of variance. And in a subsequent video, I'm going to show you how to do the calculations in two-way analysis of variance in a similar fashion, again with the objective of creating for you a reasonable level of understanding of what two-way analysis of variance is and what it means.